So welcome everyone to the second week of the QMC workshop. And today we're going to be presenting a full introduction to quantum Monte Carlo methods, and in particular the real space quantum Monte Carlo methods. I've been looking forward to this because last week was really mostly logistics and a little motivation for the workshop. And today we're going to see the real theory and algorithms at work. For anyone who missed last week, my name is Paul Kent. I'm staff at Oak Ridge National Lab, and I'm one of the organizers. And as with last week, the workshop slides are available on the QMC Pack workshop GitHub site. Everyone should have the link for that. And also we're recording this, and we'll try to get the recording up this same week, hopefully only within a couple of days. It's great to see so many people join last week. And we also had quite a few emails from people who are joining and following along on the recording because they are at very awkward time zones. So welcome to anyone on the recording. All right, so outline of today, we're gonna have a lot more information than last week. What I want to do first of all is just sort of outline the problem that we're all here to solve, the electronic structure problem, and then really go into two main ways we can solve it with quantum Monte Carlo method. So first, variational Monte Carlo, which is of course crucially dependent on the input trial wave functions. So it's important that we can improve and optimize those. So that's also a very critical step. And then in the second half, I'll cover diffusion Monte Carlo, much more powerful, but also more expensive quantum Monte Carlo technique and some practicalities. And depending on how times go, I will, of course, I'm happy to take questions throughout, but I will particularly pause after covering the Wavefunction Optimization sections just to see if we have any questions or topics to discuss. And we'll probably have a short break at that point as well, just so that this overall isn't too long. So today we're going to be covering a lot of the sort of theoretical background. And then just a reminder, so next week, we're really going to be getting up to speed with practical calculations. And so we'll be dealing with computational workflows and also the crucial topic of statistical analysis. And Jaron Krogel from Oak Ridge will be presenting that. I'd like to thank him also for co-hosting today and keeping an eye on the chat and questions. So thanks, Jaron. So of course, next week, we will be using the workshop virtual machine. And I've seen through the Slack that a lot of people are up to speed with that. If anyone still has problems with that, please discuss that and we'll do what we can to help. All right, so let's get underway. Now, this, of course, is we've only got a certain amount of time today, so I'm going to be able to give sort of a high-level introduction to the methods. So the question is, where can one find more information? So here I'm going to list a few books and sort of a few review articles and citation papers for quantum Monte Carlo codes that one can use to get into the literature. And so my recommendation would, of course, just be to look at what you've got available to you and find one that has, a style that you like. And then, of course, one can work into the literature as needed by following the references. So first, two books. This first book is the Interacting Electrons book by Richard Martin, Lucia Reining, and David Seppele. Is the follow-on to Richard Martin's electronic structure book that probably a lot of people here already own. So there are several chapters on quantum Monte Carlo in this, although the book is not dedicated to quantum Monte Carlo. The most recent book I'm aware of that's really fully dedicated to quantum Monte Carlo was published a couple of years ago by Becker and Sorella, and perhaps a university library might have a copy of that book. So how else can one get into the literature? Well, one review paper that I'd really recommend everyone take a look at is what's really a classic citation in the literature. This Reviews of Modern Physics by Matthew Fulks and co-workers. It's published back in 2001, so it's missing some of the newer methods that we'll be touching on in this workshop. But I feel it's got a very friendly introduction to the methodology and some perspectives in there that are still very worthwhile. This article is really focused on solid state calculations. That's in the title. Of course, a lot of other review papers have been published since, and I'd highlight this chemical reviews by Mestevetsky from a few years ago, which is on essentially weak interactions in molecular systems, so van der Waals. And this has a shorter, but still very approachable high-level introduction to quantum Monte Carlo, as well as a description of the applications and the choices that need to be made to get accurate results for molecular systems. Another route in is to go via the citation papers for the different quantum Monte Carlo codes that are out there. So here I list the one for QMC PAC, published in 2018. It's in the Journal of Physics Condensed Matter, and this is open access. So you don't need a subscription to the journal to read it. And of course, it's got some citations to the newer methods and newer applications. We also wrote a review paper last year in the Journal of Chemical Physics. And if you go to this issue of the journal, I would recommend taking a wider look at the articles in it. It's got a special issue on electronic structure software. So there are papers by authors of other QMC codes and also actually other electronic structure codes in general. So I think that's actually a very good issue of the journal to get into the many-body electronic structure area. So what are we here for? Well, in common with, I think, the rest of the electronic structure theory community, one of our dreams and goals is that, we can solve the quote-unquote electronic structure problem. And one definition of that is that we can solve the zero-temperature Schrodinger equation, not just for a model Hamiltonian, which can already be difficult enough, but to do this for a general molecular or solid state system and assemblies of them, and of course do it exactly and cheaply and so on. And of course the ramifications of that would be substantial because we could get the properties of these systems, have a much better understanding of how they behave without having to invoke additional unknown approximations, which we have to do today. And of course, these methods don't exist yet because this is a very difficult problem. So let's review, why that is. So, we're here to solve the Schrodinger equation H psi equals E psi. I guess I could write psi 0 here for the ground state wave function. What is the Hamiltonian? Well, of course, it's the kinetic energy piece, kinetic energy of the electrons. We then have the electron ion term for interaction of the electrons with the ions. And then we have the Coulomb interaction between all the electrons. So this is the sum over all pairs of electrons. And of course, this is a long range sum. It's over all electrons in the system. And this, of course, is what gives rise to a lot of interesting phenomena, correlated phenomena in molecules and materials. So that's already a challenge. But an additional challenge comes from treating the fermionic nature of the wave functions correctly. And in wave function language that we're following here, there's a very important symmetry that we need to make sure we respect. And that is if we write down the wave function as a function of the n electron positions, well, if we swap the location of any two electrons, then the wave function must change the sign, but not otherwise the magnitude or in any other way. And of course, that's a very difficult symmetry to have for any combination of the pairs of electrons. And actually, Troy and Weiss back in 2005 showed that, at least for fermionic quantum Monte Carlo, solving this would fall into a mathematical class of problems, non-deterministic polynomial hard, which means, translating that, if we assume that this applies generally, that we're not going to be able to find a polynomial scaling or non-combinatoric scaling that's exact. So what we really need to do in this field is have methods that are, of course, as accurate as possible, but allow us to sneak up on this problem and converge it in a controlled manner. And so just to provide some perspective on this, I thought to provide a sort of a little sketch of how I think of the two quantum Monte Carlo methods that I'm going to be covering today. Because sometimes quantum Monte Carlo is described as one method, and of course it's not really. It's a whole class of method, and they actually all have their own variations within each. So what I'm sketching here is some sort of a plot of the accuracy of all the properties. So not just one property, because we could maybe empirically fit that, but we want all the properties to improve towards some sort of exact result. And of course, inevitably, to get more accuracy, the cost is going to increase. And of course, it's also worth mentioning that there are on the books some methods that would formally get to this top right corner, or at least this top edge. And that would be, for example, full configuration interaction in an infinite basis set. And of course, that's far too expensive to afford. Just for reference to some of the density functional theory discussion, the top of Jacob's ladder is, of course, at the top here. And so there's other ways to potentially climb up here. So today, I'm going to be covering variational Monte Carlo with essentially sort of fairly simple trial wave functions. And okay, they're on axes here, but I'm going to show you all that this is actually already quite an accurate method. We can use it for full production research calculations today. And also diffusion Monte Carlo, which is more costly and of course more accurate as well. Maybe it's at least more order of magnitude more expensive. But these, of course, are not uniquely defined methods. As we're going to be describing, we've got choices on the trial wave function. And what the community is working on tackling actually is how to improve these wave functions in controlled ways so we can move up towards steadily more accurate results. And of course, although we often take questions about quote unquote, how accurate are the methods, that's looking along this axis, what is achievable, I think it's also worth thinking about this axis here. So if we have a certain amount of computer time, or more realistically, we're prepared to spend 2 months of our own time studying a particular research problem, what can we achieve? What methods are in scope? So in this sort of sketch, we could use diffusion Monte Carlo and improve it a little bit. Now, one method I'm not going to be talking about that probably everyone here has heard of, even if QMC is completely new, is the method that was used back in 1980 by Seppeli and Alder for their homogeneous electron gas results. And that used so-called release node quantum Monte Carlo, so it's formally exact. But the problem is this falls into the category of one of those methods that's on the books, but it's so impractically exponentially scaling that it can only really be applied for the comparatively simple system, such as the electron gas. And of course, that's unfortunate. But today we'll see that we can make steady progress with variational and diffusion Monte Carlo. So let's move on to solving this problem. And I'm going to introduce the variational approach and then variational Monte Carlo. So the question is, how can we go about solving the Schrodinger equation, in a full and many-body way with controlled errors and approximations? Well, one way that we probably all did in our first few quantum mechanical lectures is to use, the variational principle. And so what that says is that, if we take some trial wave function and we evaluate its energy, we know by definition it's going to be above the ground state energy. And if it is equal to the ground state energy, then it is the ground state wave function. And of course, this is the basis that we can use to construct a variational methodology. And of course, the key thing built into the name and the methodology is that we're going to need ways to get trial wave functions and improve them variationally. So that's really going to be key. If we couldn't get good quality trial wave functions, this wouldn't be very practical. Now, I think it's worth mentioning that there's actually no requirement to use a statistical approach at this point. But to do otherwise, actually, it's very expensive, much too expensive to afford for more than a few electrons. And that's because if we're to do these integrals with standard numerical integration, such as Simpson's rule or maybe a more sophisticated, Gaussian integration approach, then those methods have a cost that scales with some power of the dimensionality of the problem. So, for example, if we were to have 100 electrons that we want to simulate, and they're each moving in X, Y, and Z, so that's 300 dimensions, these integration methods would scale with the 300th power. And so, of course, that's much too impractical to afford for more than just a couple of electrons. So that's the curse of dimensionality. And Monte Carlo methods actually sidestep this. Of course, they have their own restrictions, but they do avoid this important problem. And of course, the way we do Monte Carlo integration, or one of the ways of introducing it, is to rewrite the integrals that we want to do in terms of a sum over some probability density, which we can sample. So that's what's done here. And if you look compared to up here, all that we've done is sort of insert and divide by the trial wave function. And we have two important terms here. This quantity we're going to keep seeing crop up again and again. So this is the Hamiltonian applied to the trial wave function with the electrons at some point in space, divided through by the trial wave function. And this is actually just a scalar quantity. It's an energy, and we normally call it the local energy. And what we then do is integrate it over this probability density. Now, why am I calling it that? Well, this is quantity. If we look at it, well, it's normalized because of this bottom integral. We know it's smooth and continuous. It's also non-negative, so it fits the definition. And this then means that we can use really classic important samples, metropolis methods to sample it. And so that's what we're going to do. And this will give us the beginnings of variational Monte Carlo. Right, so how do we do this? How do we sample the square of the trial wave function to get this probability density? Well, we use the classic metropolis algorithm. And I think probably everyone remembers a little bit about this. We're going to have a method that's got a random element to it. We're going to be randomly proposing moves. And if we propose a move to somewhere that's more likely, we're going to accept it. And if it's less likely, we are still going to sometimes accept it so that we can sort of explore everywhere. And so the way this maps into an algorithm is that we're going to have some loop over steps or sweeps in our Monte Carlo. We're then going to loop over every electron in our system. And we're then going to propose a move from one electron to some new position, R prime. And we're going to have some sort of recipe for doing this, some sort of transition probability. And there's some sophisticated choices for this, but also some simple versions that are still quite good. And then the key thing is that we accept this with this probability here. Now, if we pretend that this transition probability is sort of the same both ways, right? This cancels. And then we can see that, well, if we move an electron to somewhere where this top part is larger, well, we're actually, the acceptance probability is going to be 1. This will be larger on the top. If it's lower probability, well, we still have a chance of accepting that. And so this is then how we can, if we keep doing this, we're going to sample the square of the wave function, and we can evaluate properties such as the local energy. And so what do we normally use for this transition probability? Well, there's a few choices, but the standard one, which I used actually just this morning, was we use normally distributed steps, and the width is proportional to some quote unquote time step. And a key point here I want to mention is that this time step only affects the efficiency of the simulations. Right? It doesn't change the result. So it changes the statistical properties of what we're measuring and how efficiently we get them, but it doesn't introduce any errors. And just a sort of a note about a rule of thumb, the sort of typical acceptances that we're looking for in efficient simulation, might be 50%. It could also be 30% or 60%, but it shouldn't be 1 or 99. Right? That's not typically an efficient simulation. So then, how does this work inside a code? And of course, this is all implemented. We don't have to type this in ourselves, but let me just sort of talk through it because it's still a very simple, quite elegant algorithm. So we're going to generate some initial electron positions, maybe put them around close to the atoms to start with. We're then going to propose moves. We then only need to evaluate the wave function at the new position. We then do that accept, reject step. And we update the position if we accept, and also update any bookkeeping that we need to do along the way. And then we recompute the energy and indeed any other properties that we're interested in, maybe the electron density, perhaps a pair correlation function. And of course, to make a code like this efficient, one takes care not to recompute things that haven't changed. So all the production QMC codes do very careful bookkeeping to make this efficient. And we then loop around for every electron move, and then we sweep for some number of steps. And then that's what the code does for us. And then, of course, we have to analyze the results ourselves. So what are the key properties we're going to be looking at? And we'll be seeing more of this over the coming weeks. But of course, the key quantity is the variational energy, and that is the mean local energy, or the mean energy we get through the run. And that's nothing more than this average, right? Total the energies divided by the number of samples that we had. But that's not the only property we're interested in. We also need to measure the uncertainty and report the uncertainty in this energy. And we do that through the variance and the standard error of the mean. So these are standard statistical analysis, assuming a normal distribution. So we measure the variance of the wave function. And so this is a measure of the squared, essentially the spread or distribution of energies that we get in our simulation. And actually, we're going to see later on that this will become smaller as we have better trial wave functions. So we get the variance. And then, the formal mathematics here is that the uncertainty, the standard error of the mean is given by the standard deviation divided by the square root of the number of samples. So that gives us our error bar. One thing I'll note here, and again, we'll be revisiting this next week, but of course, this analysis assumes that all the samples are statistically independent. And if one can imagine, if we were to make tinier and tinier steps in our Monte Carlo, then those samples will start to become dependent. So we'll have to rescale those numbers according to how correlated our statistical samples are as we go on. So now a key note on the convergence of Monte Carlo. If you noticed on the previous slide, reporting the standard error of the mean, this is actually a key difference in all quantum Monte Carlo, or all statistical Monte Carlo approaches from conventional numerical electronic structure methods that we might be more used to. And that is the error bar converges with the square root of the number of samples that we have. And equivalently, that's equivalent to how long we've run the simulation. And that has some important consequences. And I sort of try to show this here in this sort of sketch. So in this sketch, we computed an error bar of 2 in our simulation, which had 100 Monte Carlo steps. Now, if we want to halve this error bar, we now have to run 4 times as long because of the square root. And of course, if we actually don't get that magnitude of reduction, and when we actually do this simulation, then we know that perhaps the simulation wasn't fully equilibrated, something along those lines. So of course, a 4 times reduction, a 2 or 4 times reduction, we might be able to afford. But notice here, if we wanted a 10 times reduction in the error bar, that's going to cost us 100 times. So that might not be affordable. So when planning and how to apply and where to apply Monte Carlo, looking at what the achievable error bar will be in our sort of budget is really important. And that, of course, refers back to that map that I showed earlier. Because one additional advantage, of course, is that once we have at least one point here, we can compute the cost of getting to our desired error bar. So now there's a question, where do we get our trial wave functions from? And there's an awful lot on this slide. So this is sort of meant to be used as a reference, but I'm going to spend quite a bit of time on it. And the key thing to remember here is we want to start with the best possible input to our quantum Monte Carlo. So we want to take the best available wave function from whatever mean field or correlated quantum chemical calculation that we can run on our system, right? And then we're going to ask the quantum Monte Carlo to try and improve it. It doesn't make sense to ask it to improve, an underconverged result from some mean field theory. So for example, this means we should use good basis sets in these calculations. So we're going to be taking the best trial wave function that we can get from PyCF or Quantum Espresso, for example. And then actually we're going to be multiplying it through by a real space correlation function or Jastrow factor. And this is actually how we improve on the quantum chemical or DFT results faster than perhaps those methods could do directly. So this correlation factor is a encodes real space electron correlations, electron ion correlations. And essentially what we can do here is build in any desired physics or electron correlations directly and have those in addition to whatever we're getting from determinant parts of our wave function, which we're going to get from Hartree-Fock, DFT, or the quantum chemical result. And let me talk a little bit more about this first, because this is one of the things that's special to real space quantum Monte Carlo. So what we can do here is do things like improve the shape of the wave function as electrons come close to each other, so near the cusps. The wave function should be sharply varying at that point. And that's something we can describe very efficiently with a simple polynomial, for example. And so what is normally used here is a sum of some polynomials. I'm going to show some examples of this in the next slide. But what we have is some function of electron-electron positions, some sum of electron-ion positions, and then maybe a three-body term involving electron-ion and electron-electron positions. And this is the form that was proposed in the Casino group. And I'll show what we're using in QMC pack on the next slide. So this is a very efficient way of building in physics and electron correlations. Now, what do we do on the left part? Well, the left part here, this is the fermionic part of the wave function. And here, this is where we're going to be taking the best input that we can get from available electronic structure codes. So what I'm showing here, this is maybe a single determinant. So this might be a Hartree-Fock determinant, for example. And perhaps we just stop there. That's already enough to publish on in many systems. But if we have the luxury of being able to do configuration interaction or some sort of multi-determinant expansion, that's sort of what's shown here. So we can choose different complexities depending on the system we're interested in and choose appropriately for the accuracy that we need. So this sort of little menu here shows sort of a progression from sort of standard starting point to sort of the real top level state of the art. So the starting point for solids in periodic boundary condition-based calculations is actually one of the most straightforward, because there we normally start with a determinant of orbitals from density functional theory. Of course, the results are testable because this is going to be a variational method and lower energies are better. But one thing we've learned is that functionals involving some exact exchange, such as HSE or PBE0, tend to produce better orbitals. Also, DFT plus U can be used. And of course, one can get up to tricks involving optimizing the U, for example, to improve our QMC trial wave functions. Otherwise, current meta GGAs and GGAs and so on are also all good sources. for wave functions. And if you look through the literature, you'll see there's quite a spread of different inputs that are used. And the important point about this starting point is that a single determinant has those required fermionic symmetries that we need to build into our wave function. So if we switch any two electron positions, we get a minus sign. And if you haven't seen that, I suggest trying that on a whiteboard later today. Write out a determinant of orbitals with electron positions and see what happens if you swap electron positions. Now, for molecular cases, we might actually do something very similar to solids. We could still start from DFT. We could do Hartree-Fock, or possibly, if it's small enough, we can do something that's more sophisticated. And so this is what is tending to be done nowadays, where we would take a multi-determinant expansion from a configuration interaction calculation, for example, or a complete active space calculation. And the idea, as we're going to cover over the next few slides, is that these wave functions have a lot of coefficients in them, such as the expansion coefficients of the determinants shown here. And we can then begin to vary these and optimize these in the quantum Monte Carlo, in the presence of this Jastrow factor, which wasn't there before, of course, just to improve the wave function. And the full, state of the art, what one sees at a QMC conference, is the case where every coefficient in the wave function has been re-optimized and adjusted. So that, for example, all the orbital coefficients, the determinant expansion coefficients, and whatever coefficients were put in this Jastrow function. And that's an important step because it then means that wave function isn't dependent on the starting point, and is wholly defined within quantum Monte Carlo. Of course, one does wish to use the best starting point one can get hold of to make this as efficient as possible. So that was a lot of possible complexity. Let's look at some example Jastrow factors that we might be using actually later in the workshop. And so what I'm showing here is actually one of the standard choices we use in QMC Pack. It's actually very efficient. And what is done is to represent the electron-electron, or the two-body term, and the one-body term, so that's the electron-ion terms, simply via numerical splines. So points on a grid, and we then interpolate through them. So of course, they are represented under the hood by some polynomial, but we don't focus on defining a special form of polynomial and just rely on the splines to handle this. So then all we need to do ourselves is decide how many points we want to have that we're going to optimize. And of course, we need to also have some sort of cutoff for this. One thing to note, actually, for any Jastrow factor is because, of course, the physics of two electrons coming close to each other depends on the spin of the electrons. This part of the Jastrow factor is actually always kept spin polarized, and the rest one can choose, whether one has a magnetic system or not. So actually, I added this plot this morning, so hopefully I didn't make any mistakes plotting it. So this shows an example actually for a calculation of all electron C24, so a carbon sheet, I think. And what's shown here is just the radial components of these functions. And at the top here, this is the electron-electron part. We see a very smooth form. And this is the electron-ion part. And we see it's got a little bit more structure to it. And in this example, there was a 10 atomic unit cutoff, and 10 points were taken for each. So there's about 30 parameters in this wave function that we're going to seek to optimize. And also we can see here, this electron-electron part is very smooth. So maybe we didn't need all those 10 points, whereas this electron-ion part, well, it's got a little bit of some wiggles and structure to it. So perhaps we did. Maybe we could try a few more in that case and see if that improves the results. So that's an example of a very standard Jastrow factor that one can use in production calculations today. So now the question is, sort of the next step. We can calculate the energy of a trial wave function, but how do we get that trial wave function and improve it? So now I want to talk about a wave function optimization. And I added the word stochastic here just to remember that we're going to be doing this in Monte Carlo. And so, a simple gradient-based optimization is going to run into some difficulties. We need to be a little bit more sophisticated. So the problem we're trying to solve is shown here, right? We have some wave function, and we've decided how many coefficients or parameters in it we want to optimize in our variational Monte Carlo. And for the problems in this workshop, that's probably going to be a few tens of coefficients. And we then want to vary these to find the quote unquote best wave function. So then the question is, what is the best wave function, and how can we, what properties are there that we can sort of exploit to make this good wave function? Well, of course, the top level thing that we should be trying to improve is the energy of this Jastrow wave function, or variational Monte Carlo energy, which we're going to try and make as close to the lowest we can possibly make it. That will make it close to the ground state energy. Now, because one problem here is that if we're doing an arbitrary system, we don't actually know what the ground state energy is. So it's hard on the basis of just energies to know how good a trial wave function there is. And fortunately, there's another property that we can look at, and that's the variance of the energy. And we're going to actually, I'm going to explain variance minimization, which is now an older optimization strategy, but that exploits this feature directly. And of course, the feature is that the variance measures the spread in energies that we get in the Monte Carlo. And of course, if we put in an exact eigenstate, it actually doesn't have to be the ground state, but we'll put in the ground state in this case, then this term here is going to be E0, but also this term will be E0, because wherever we put the electrons, where we have an exact wave function, we're going to get the ground state energy. So then this variance becomes 0 if we have an exact wave function. And then this is really convenient, because we know then that as the variance of our wave function tends towards 0, it's getting better and better. And we know we don't need to know the energy for that. So even though the main production route for doing wave function optimization is not variance minimization, it's still very important to keep an eye on the variance of the wave function, because it gives a measure of the quality when we don't know what the exact results are. So now let me introduce variance minimization. And actually, when I was putting this slide together, I struggled to find a very recent publication with figures that I can show, because there are indeed better methods to use now. But there are some still recent and very relevant papers. And when this is applied, there are some sort of key tricks for efficiency that actually every QMC optimization method has to use. So of course, this slide is designed to be read, but let's go through a little bit of it. So of course, we're going to do an optimization method. So of course, we're going to use sort of a textbook numerical optimization to do this. And we're going to set about reducing the variance of the wave function. So the obvious thing to do here, and this was realized very early on in Quantum Monte Carlo, is we need to do a VMC run, and we're going to save out some configurations all the way along the run. And then we are going to vary the parameters that we're optimizing, so P prime, and recompute the energies. And of course, the key thing here is that if we had to do a wholly new VMC run with this new parameters, this would just be very expensive, and we wouldn't have a practical method. And the key trick is that we can properly weight the probabilities to the correct probability distribution for these new parameters with simple factors that look like this. So what we can actually do is do this initial run, and then during the optimization, as the optimization algorithm considers different parameters, we can recompute the energy very efficiently by rewriting the formulae, including these sort of reweighting factors. And this makes for an efficient procedure, and actually every optimization scheme is going to do this. Now, of course, we do need to repeat the outside cycle a few times, because one can imagine, if we make a big change to the wave function, then our statistics are going to become less good. So it's important to regenerate and iterate a few times. And I'll show an example of this. Now, I wasn't able to find a recent figure showing the effectiveness of this scheme, but I did find a study here showing something that's actually very important that will carry through to the other optimization schemes. And that is the question of, well, how many configurations do we need? And so this paper has a study of an optimization scheme focusing particularly on the variance. And what's shown here are results for an all-electron neon atom, and this is just one parameter, so one Jastrow parameter against the variance, obtained for varying numbers of configurations. And what we see, if we only did 10, and that obviously feels like a small number immediately, you can get the variance in the wrong place here. And so probably that's not going to be very successful optimization. But by the time we start having 100 or maybe 1,000 configurations, we can sort of properly resolve where this minimum in the variance is for this parameter, which apparently should be 0.02 or so in this case. So the takeaway here is that even for a relatively small system, we need thousands of configurations here. So that's something to bear in mind for efficient minimization. Now, since this is just a review talk, I'm only going to present one more optimization scheme, the main production one that I think everyone in the field is using now, but I think it's worth mentioning that there's a whole zoo of different approaches that have been proposed. And perhaps, one day someone, reinvestigates these and, finds that they can be improved over what we currently use today. So what do we use today? Well, the method that I think everyone in the field is using is so-called the linear method, sometimes also called energy minimization. And this is a real breakthrough back in 2007, because it's an algorithm that makes it possible to not just directly optimize the energy, but do this for general parameters or coefficients in the wave function. And so this means that one can optimize orbital coefficients, for example, determinant expansion coefficients, where the variance minimization that we quickly went through just now would really struggle for anything but a really simple case. And there are two key steps in this scheme. So the first is that there's a sort of a linear expansion of the wave function that's done sort of in parameter space. And then we solve a sort of Schrodinger-like equation or an equation that's very similar to sort of any electronic structure solve. And behind the scenes, there are a number of very important numerical, I won't say tricks, well-considered considerations to actually make this diagonalization stable. And of course, one solves this and takes the lowest and takes the the 0th eigenstate that comes out as the ground state wave function. And in practice, this turns out to work very robustly, and it's now the standard method. And it can optimize all parameters in the wave function, at least if you give it enough statistics and so on. So let me show you now some results from the paper. So they looked at carbon-2, amongst others, which, as we'll see soon, is actually not necessarily a very easy system to study, high accuracy. And so this is energy against iteration in the optimization. So this is the outside cycle that I mentioned. And we see this nice progression. So here we have the results on the first 0th cycle with initial error bar. We get a big step down in energy, and then it keeps systematically improving until it starts bouncing around in the statistics. So I think this is one of the first times this sort of convergence had been shown. And one thing to note here is that this, in this initial optimization, they have 10,000 configurations. And as they want ever more accurate results, you of course have to increase the number of configurations. They went up to 400,000, of course, paying appropriately more in that case. And then another important analysis that was done, and I'm going to go over this because of course it carries through to other molecular systems. We can show this ourselves. Another thing that was shown was that the convergence with the number of determinants in the wave function. And again, this shows, referring back to that map I showed at the beginning, how we can improve on a single determinant wave function. So this again is with, this is carbon 2, variational Monte Carlo, just optimizing the Jastrow factor, gets us a result here. And then as we add determinants and optimize the coefficients in front of them, sorry, first of all, this is just the Jastrow factor. This next point is as we add determinants and optimize the coefficients in front of them, we have this dashed line here. And we see this is actually a huge improvement in the energy. And this actually gets us more than half the way there, even to the diffusion quantum Monte Carlo result. And then finally, one can also optimize all the orbitals, and that improves further. And we haven't got to diffusion quantum Monte Carlo yet, but one thing to note, of course, diffusion quantum Monte Carlo is more accurate and more expensive, but using this optimization method, variational Monte Carlo is able to beat diffusion Monte Carlo with some of the simpler trial wave functions. So it is possible to have a very accurate VMC trial wave function, if one works hard enough at it. So that's the background of the algorithms. Let's now consider a little practical matter. How can we map this to computers? And this will have relevance in diffusion Monte Carlo later on. So how do we map this to our computers? Well, we want to run this efficiently. So of course, one thing we don't do is try and distribute out our electrons over the many compute cores or a large supercomputer that we might have today. What's done is to put independent Monte Carlo walks or Markov chains, or walkers, as we tend to call them in the field, on each CPU and let them evolve independently. And what tends to be done, I mentioned this as sort of the practicality, is to actually subdivide the run for convenience into blocks. And then we're going to be writing out summary statistics, averaging over all of these results on different cores at the end of each block. And this, of course, isn't a huge efficiency saving for just the energy, because the energy is a scalar quantity. But by the time one starts measuring the electron density or the density matrix, this is actually quite a big saving and important to do. So now, what does our variational Monte Carlo workflow look like? And we're going to be running this, start to run this next week. So the first thing we need to do is generate the determinant part of our trial wave function. And we do this by doing the best density functional or perhaps correlated quantum chemical calculation that we can afford, and that we have a code available to do. So DFT in a large basis set, quantum chemistry in a large basis set. Then we're going to choose a Jastrow function, multiply through by that, and then we do the optimization step. And I want to stress, I've shown some advanced examples here, but we can just do the Jastrow part, particularly if we're going to go on and do diffusion quantum Monte Carlo. Of course, the trend in the field, as I've shown, is to optimize increasingly more of these, to have standalone wave functions that don't depend on the generating method. And then, of course, the last step, when we have sort of our gold trial wave function, the best one that we can make, we do our production variational quantum Monte Carlo. And the first time we go through this, and this is exercises that we're working on through the workshop, is that we need to do things like choose the time step and maybe try some different Jastrow functions, for example. So that's the theory. Let me now show some example results from the literature before sort of summarizing what the pros and cons are of variational Monte Carlo. So this set of results is for first row diatomic molecules, and it's actually one of the follow-ups to the linear method paper. And what I'm showing here is results for the carbon-2 molecule with single determinant, then the carbon-2 molecule with multi-determinants, so more expensive, more sophisticated wave functions. And then at the end, we'll talk about the results for a range of different molecules and how efficiently we get the binding energy or the depth of the well. So what we're looking at is energy against a distance or bond length in the molecule. And this first red curve is, there's no actually Monte Carlo here. This is restricted Hartree-Fock. And we also want to compare against the black curve, which is a Morse potential fit to experimental spectroscopic data, very accurate experimental result. And of course, we want to be able to resolve the position of this minima and the depth of this minima accurately. So now we do variational Monte Carlo, the Jastrow single determinant, and we get this result here. So we get a very big improvement on Hartree fog, but we still see there's a little bit of energy to go. And we can see that diffusion Monte Carlo with just a single determinant also improves on this, but there's still further to go. To really do a lot better in this case, this is not a particularly easy system, one has to do multi-determinant wave functions. So here, the red curve is a complete active space calculation from chemistry, and we see that the minima is now a little bit better produced, and the energy scale here is much better. So the minima is much closer to the experimental one. And now, when we do a variational Monte Carlo calculation and re-optimize all those coefficients in the wave function, we see that just the VMC wave function is actually really good, right? And that even may already be enough accuracy. We can go on and use the projector methods I'll be describing in the second half of this presentation, and that actually improves further. Now let's see if that's a general result. So here we have the error on the well depth, so we'd like to be 0 for lithium through to neon 2, and just some perspective. Here's a multi-configurational SCF calculation in this green. Apologies, these points are a little bit hard to read, but we see that can have errors of in the 1 eV range in this case. If we then do variational Monte Carlo, well, we're just one determinant, that's not necessarily a whole lot better. But if we add multi-determinants, that's actually a big improvement. And then finally, if we were to do diffusion Monte Carlo, that can really clean us up and we can get very accurate results in this system. So those are results in some molecular systems, and we could actually do some calculations like this during the workshop. And I'd now like to show some sort of more advanced calculations, because I don't want to leave people with the impression that we immediately drop variational Monte Carlo when we have diffusion Monte Carlo available to us. There's some very good reasons why one might use the variational Monte Carlo approach for production research calculations. And two main reasons for this is that we have the form of the trial wave function. So we can do additional integrals over it or measure observables, other properties of the wave function more easily than in other methods, such as diffusion Monte Carlo. And we can also do things like input novel wave functions that encode some physics. So in this case, pairing. So let me show these sort of two examples. Well, here on the left, this is the pair correlation function for electrons in silicon. I showed this last week. And so what we're looking at, this is the 110 plane in silicon. We're standing on this point on the bond. And this property shows us how far we have to go till we find another electron. And we see there's some structure here, so we can learn something about the properties of electrons in this system. And the key thing about this is that to compute it, one has to do an additional integral over the electrons using the trial wave function. And so that's most straightforward, done and analyzed in variational Monte Carlo. Now, a much more recent result from Casula and Sorella, this is the case of applying actually a full ab initio attack on the iron selenide superconductors, actually looking at pairing them and the structure, the various properties that result, and actually explaining quite a few experimental mysteries about the system, all directly with quantum Monte Carlo. And here, their largest calculation, if I read the paper well enough, it was about 350 electrons, and they're optimizing 10,000 different parameters. So that's a real state-of-the-art application, but also it has state-of-the-art results. So finally, before I pause to take questions, and I think we'll have a little break as well, let me try and summarize the pros and the cons, or the advantages and disadvantages of variational Monte Carlo. And some of these actually are common to other methods as well, but I'm going to say them here. So on the plus side, we have this explicit form of the trial wave function, So we can use any trial wave function that we can think of, and we could be motivated by physics and chemistry, just as was done in the iron selenide case. And we also don't have to worry about doing conventional numerical integration over the form of this wave function. Provided we can compute the value and the derivatives, we can use it in the Monte Carlo. So that's a huge strength over traditional numerical approaches. As I just showed you, we can compute any observable from the trial wave function. And also, this is something I find very appealing about the method, right? It's actually very simple, very elegant. The Monte Carlo algorithm is very simple. And importantly, we didn't introduce any sort of time step errors or other sort of discretization when we did this. And one thing I should mention here, this is common to other QMC approaches as well, but the scaling with system size, at least the nominal scaling with system size we have so far, is cubic. And that comes from updating the determinants that we have in our wave function. That's a cubic cost. All right, so there's lots of pluses, but let's look at the negative column as well. So one disadvantage is actually the same as the advantage, right? We have this explicit form of trial wave function. So we can use any trial wave function that we can imagine. But what if our imagination isn't good enough and we forget to include some important physics or chemistry in the trial wave function, right? That would be a problem. We could get the wrong result. Also, if we start now to apply this to different systems, very different systems, it can be quite challenging to have consistent accuracy between the different systems. And so error cancellation between properties may not be so good. And so that's actually a reason why we'd like to have a more accurate method that's not so dependent on the input trial wave function. Another very definite issue that we just can't sidestep here is that while optimizing wave functions with only a few coefficients or parameters in is now, I would say, relatively straightforward, to do tens of thousands is still a real challenge to do reliably. So this is not yet sort of fully automated and push button. That's something everyone in the community, I think, is working on, would like to see happen. But that means that some of these top level applications require quite a bit of hand holding. And that's something that we would like to get away with, like a method anyone that could run, or that we can run in a fully automated manner. And finally, and this is true actually of other many-body methods, not just quantum Monte Carlo methods, but when we do periodic calculations, so solid state calculations, and we'll be revisiting this in a few weeks, we need to do finite size scaling and progressively larger calculations, because if we just run a small primitive cell, then the electrons in the primitive cell are going to see their periodic images, and they're not going to be very far away. So that's not physically realistic, and one incurs finite size error at that point. So one has to do larger and larger cells. And of course, even with cubic scaling, that still adds up quite quickly to the cost. So that's a special factor for solid state calculations. Of course, that's not a concern for molecular calculations. So those are the pluses and minuses. I think I've gone through everything I want to touch on in Variational Monte Carlo at this point. So I'll be happy to take maybe sort of the 2 or 3 most important questions, Jaron, and then I think we'll have a short break.
Okay, so we've had a couple questions come in. First one from Nikhil. Question is, if we are using wave functions from DFT, does that mean that the wave functions in QMC also have a pseudopotential character?
So that's an excellent question, right? And I skipped over mentioning pseudopotentials in this talk, and we're going to have a whole dedicated session on those later on. We can choose in quantum Monte Carlo, just as you can in density functional theory, actually, whether or not to use a pseudopotential. And it's sort of similar considerations, right? If they really affect the properties of your system, then at some point you have to run an all-electron calculation. So actually those Jastrow functions I had a plot of were from all-electron QMC calculations. However, as we'll see later on, QMC has got a large power scaling with effective atomic number. So we are definitely interested in using effective core potentials whenever that is practical and sufficiently accurate. Good question.
Okay, next question. Does the concept of K-points hold in QMC calculations, given that we're no longer in a single particle band theory framework?
Another excellent question. And I think the answer is no, not really. As we'll be seeing in a few weeks when we evaluate periodic calculations, we do have to consider something similar. And that is, when we do convergence, which is the first thing I think of with K-points, particularly for metallic systems, we have to average over twist boundary conditions for the wave function. And those are, I think those are a little bit similar to K-points, but they're not exactly the same thing. So we do have some similar considerations, but of course we're in a many body framework now, so it's different from the single particle framework.
Okay, do you have time for a couple more questions?
Yep.
Okay. From Roman Fanta. Is it possible to optimize the orbitals in the single determinant wave function in VMC, for example, with QMC pack?
So the question was about, what can one essentially optimize in the trial wave functions, and actually optimizing the orbitals in a single determinant, we think is probably a very effective way of improving the trial wave functions and making them sort of independent of the starting method without incurring, the huge cost of, let's say, a large multi-determinant expansion. So some orbital optimization, as it's sometimes called, has been done with QMC pack. And if you put a note in the Slack, I'll remember to follow up with a link to that paper on iron oxide by Joshua Townsend. And actually, we're currently working on re-architecting and re-implementing the orbital optimization within QMC pack, because as was shown, for the C2 case, one can, let me just go back and see if I can find it. It's a little bit dangerous here. All right, so for example, if we look in this case of C2, optimizing the coefficients in front of the determinants, which is something that we can do, and that can do routinely, that gets us a lot of the way there. But to get the final step, one certainly wants to optimize the orbitals. And this is a system where actually the initial orbitals with C2 are quite good already. So yes, that's something we're very definitely working on. Okay. Maybe one last question, Joan.
Okay. In principle, Jastrow functions containing natural logarithms could be added, correct? That could change the nodes of the wave function, right?
So let me go back to the form of the wave function. I maybe said this a little bit quickly. So the form of trial wave function I touched on here, and of course there are others, is that we have this fermionic part with the determinants here on the left, and it could just be one determinant of Hartree-Fock or DFT orbitals, right? That would normally be what we use in solid state. And this is the part of the wave function that has the zeros and the nodes in it. This is to make connection with diffusion Monte Carlo we'll be covering next. And this exponential in front of the Jastrow factor means we don't change the zeros. Now, of course, one could consider other forms of wave function where one modifies pieces here, or even uses a different form entirely, as I think was suggested, to vary the nodes. So yes, that is something that could be done, and I would consider it, that's essentially a research topic. And actually, that's one of the areas where I really hope that we see a lot of progress over the coming years, because the forms of wave function that are currently used in production QMC calculations have been fairly similar now for a number of years. And one can learn about the accuracy and effectiveness of different wave function forms, even on fairly small molecules, fairly simple systems that would be cheap to run. So it will be interesting to see what happens with different wave function forms. And through, of course, the variational principle, we know that if that gets lower energies, and it's easier or more compact, there's fewer parameters, then that's actually a better wave function. I think a lot of people will be keen to use them. All right, so I'd now like to move on to the sort of second half of this presentation, touching on the diffusion quantum Monte Carlo method. And then we'll touch on a few practicalities. So why diffusion quantum Monte Carlo? Well, as we touched on in the last session with variational Monte Carlo, it'd be useful to have a method that is less dependent on the input trial wave function. And that's what diffusion quantum Monte Carlo is and does. And it's a flavor of so-called projector quantum Monte Carlo methods. And what they do is take an input trial wave function and try to, and aim to systematically improve them by projecting out the ground state. And there's a number of these. And they're all based on essentially considering the time evolution of the wave functions, and importantly, now the time-dependent Schrödinger equation. And a key trick that's done in all of these methods is to write these equations in imaginary time, so tau equals IT. Now, if we look at this equation, and again, think back to our early math lectures, this is an equation we know how to solve. Right? This is a simple partial differential equation, and we can sort of analyze this to see what's going to happen to our wave function as we integrate it over time. So if we write our input wave function in terms as a sum over energy ordered eigenstates, Ci times the phi I here, and then think what happens when we evolve with time, well, the solution of this PDE is, of course, just this exponential. So as we consider what happens at larger time, what's going to happen is that the highest energy components are going to drop out exponentially, the fastest, then the next highest will drop out, and so on. And then eventually, this will just leave us with the zero component here, phi zero, which is the ground state wave function. Of course, we have to be careful and sort of renormalize this so we sort of don't run out of wave function altogether. And that's really the basis of diffusion Monte Carlo and also the projector quantum Monte Carlo methods. So it's much more powerful than the variational methods, and it's got a more sophisticated formalism that we're going to go into. This just shows an example applying the method on the homogeneous electron gas, projecting out now in imaginary time, and we see some initial energies being steadily improved upon. And if we ran this long enough, it should just about stabilize, and then we'd start taking averages from it. And I should note one can also do a limited number of excited states with this method as well. Now, I thought briefly about including the full derivation of diffusion quantum Monte Carlo in this talk, but it's quite involved and it goes over several pages. I would encourage people to look at the derivation in the review papers that I have here at the bottom right, or in the books that I showed at the start of this presentation. So I'm going to skip over the derivation here. I think that would be a bit too much today, but I am instead going to touch on some really important differences from the QMC techniques that we've used so far. And the first one is probably the most critical. So remember, in variational Monte Carlo, we were sampling, the square of the wave function, or either the square of a trial wave function that we've input. And this is actually not how diffusion quantum Monte Carlo works. When one writes down the important sampled version, which is the version that that scales and we can use for ab initio calculations, what one actually gets on computes is this time varying quantity, which is the ground state projected wave function multiplied through by the trial wave function. And so this, of course, then immediately is going to have some consequences for computing properties, because if our properties don't commute with the Hamiltonian, so it's really anything other than the energy, we get a mixed estimator. And so there are already some immediate difficulties here. But as we'll see, we're able to get very good energies through this approach. And next, instead of having multiple walkers just for computational convenience and mapping onto computers, here we're going to represent this quantity as an ensemble of walkers. So having multiple walkers, thousands of them, is an intrinsic part of the scheme. And we need a sufficient number actually to get an accurate and stable result. Now, one thing that, of course, we didn't go through the analysis, but if I didn't make any mistakes when I copied out this formula, then we look at what the formula is for the time variation of this property is. We get terms to do with drift and diffusion of the walkers. And the key thing here is that we already have those quantities in our variational Monte Carlo code. So this just requires replumbing them in a different way. But then there's also a term here that varies the weights or the amplitudes of the walkers. And that here, and this is a key difference from the variational approach. And that is here, we're going to see, okay, if we have a set of electron positions, we have some particular local energy for this walker. And if this walker happens to have a lower energy than some reference energy, then we're going to allow it to gain weight or multiply in our simulation. And for something that has a higher energy, we're going to reduce its weight or maybe destroy it altogether. So this reference energy here is an important thing to help normalize this ensemble of walkers, make sure we don't have too many or too few. As I mentioned, this maps really well onto a variational Monte Carlo code. Just now we have a variational variable population of walkers. And one key thing that I haven't shown you here, because we haven't done the derivation, is that at a certain point in the derivation, we have to make a Trotter discretization of the Hamiltonian or effect of the Hamiltonian, and that is only accurate to the square of the time step. And so that's a very big difference with variational Monte Carlo, because in variational Monte Carlo, the time step only affects statistical efficiency, but here it's going to affect the accuracy. And so one key difference here is that, you know, as a rule of thumb, the acceptance ratio for good accuracies is going to be over 99% in our Monte Carlo. So we're nearly always going to be accepting these moves. Now, there's one other additional key step that we need to make in setting up a viable algorithm, and that's imposing the fixed node approximation to treat the fermion sign problem. And we have to do this because those partial differential equations that we just had on the last slide, they don't know anything about respecting fermionic symmetry. And so if we just evolve those, then we'll actually end up with a bosonic solution. And there are certainly applications where that's a good use of diffusion Monte Carlo, but that's not what we're trying to solve here. And so what is done then is to ensure that the projected wave function times the trial wave function is, let's say, always positive. So what we're going to do now is we're going to impose a restriction on the projected wave function that it respects the signs or the zeros coming from our input trial wave function. And this seems like it might be complicated to do, but all one does in the Monte Carlo is when you propose a move of an electron, if the trial wave function changes sign, you just reject that move. And this is sufficient to preserve a fermionic solution. So now we're doing valid fermionic quantum mechanics, but it comes with a price. And the price is we have now made a variational error in the energy. Now, I would say that's not such a bad price to pay, because by analogy to variational Monte Carlo, once we have variational errors, we can set about testing the accuracy of different trial wave functions and different nodal surfaces. And in case you were wondering, you know, hang on a minute, if we're trapping electrons in certain nodal regions, does it matter where they start? Well, fortunately, that also doesn't matter. There's something called the tiling theorem that says the exact ground state can only have one type of nodal pocket, so it doesn't actually matter where we start on Monte Carlo. So we don't have any additional worries there. Now, one might be wondering about what do nodal surfaces actually look like. And of course, they're very difficult to plot for any realistic system because they're a 3n-1 dimensional quantity. But we can look at them for examples such as in the 2D homogeneous electron gas, where we can easily do a 2D plot. So this is a result of a particular density, you know, x and y. The nodes are shown with these lines. And these green points here are where the electrons are in this particular frame of the Monte Carlo. Actually, the different colored lines here are from two different trial wave functions with different nodal surfaces that were being tested. So we can see, even this quote unquote simple 2D system has quite a complex nodal structure. So how does diffusion Monte Carlo work in practice? So what it maps onto, we have an algorithm where we have a variable number of walkers. And if the walkers are in a favorable energy location, or the potential is small or low, they're going to multiply or gain weight. And if they're in an unfavorable location, they're going to be removed. And of course, we can use weights equivalently here. That doesn't really change anything. And eventually, at the end of the day, the probability that's going to be described is, of course, going to be largest where the projected wave functions are largest. And that's shown here in this cartoon. This is adopted from the Reviews of Modern Physics article. So we have some assumed potential in this 1D example. We start with some initial set of configurations of a set of walkers. So we've got 7 of them here, apparently. And then we evolve in time. And we immediately see, okay, this walker, it's moved somewhere, which is very unfavorable. So we're going to delete it. And this other walker here, which is in a low energy state, we're going to multiply it, split it. And so if we then evolve in time, over time, we are going to gain this representation of the fixed node wave function. So that's how the sort of algorithm works at a sort of a high level. Now, if we look at what that means in terms of energy, because we can actually see this for real ab initio calculations, we start with some initial energy of the trial wave function, we propagate in time, and the energy should go down quickly as we project out the excited states. And then we should start sampling the ground state, or the fixed node ground state in this case. And we then run for a long time and take averages of the energy and other properties along this path. Notice, of course, that this is above the true ground state energy because of the fixed node approximation. One thing that I'm going to mention the code sort of do behind the scenes is they update this reference energy we had in the formulae to keep the population under control. What does that look like in practice? So with real data and not a cartoon. So what I'm showing here in this figure are published results for bulk vanadium dioxide from Ilkka Kalempa, published in Physical Review Materials a few years ago. And this paper has, in the link through in the published data, it has all the inputs and outputs of the simulation. And in this case, it has 200 electrons. The time step was 0.01 atomic units. And the wave function came from a DFT plus U calculation, and the U was varied to optimize the DMC energy. And here we have energy against step or time. And we see that here for real, this initial equilibration or propagation out of the excited states, we now start sampling the ground state within certainly 100 or 200 moves. And then we keep running. And in this simulation, there were 8,000 steps for 3,000 walkers to get sufficiently small error bar for the quantities of interest. So that's a real diffusion Monte Carlo algorithm. Now, importantly, we need to look at the time step errors in our calculation. I mentioned in diffusion Monte Carlo, this is actually a source of error, whereas in variational Monte Carlo, it just affects the efficiency. So what we need to do, and we'll be touching on this in later weeks of the workshop, we need to either compute our properties at a number of different time steps and extrapolate to 0 time, or simply use a small enough time step that the errors are sufficiently small. And I show 2 examples of this here. So one here on the left, these are results for bulk silicon. So we have energy against various time steps. Notice this is a log scale, and eventually we do a best fit to shoot through to 0 time step results. And I draw attention to this paper because in this paper, there's an attempt to actually control and understand all the errors and biases in the calculations. And then here on the right, we have some an earlier work looking at zinc selenide and zinc oxide. And here we have time step against energy. And this is just a hint of what's going to come when we learn about pseudopotentials and their use in quantum Monte Carlo, have two different approaches for treating pseudopotentials in diffusion Monte Carlo, and those are extrapolated to 0 time. So this is really a crucial step in these calculations. Now, how do we map diffusion Monte Carlo onto computers? Well, of course, this should be fairly straightforward. We're going to pick a target population, and we're going to put many walkers or Markov chains on each core. And we're going to be updating that reference energy every step to keep the population under control. Now, for the scale of calculation we're doing in this workshop, we don't really have to think about this next point, but just to mention, if one starts doing larger calculations on hundreds or thousands of cores, then it's important to think about load balancing of these populations, because if we have a different number on each core, then obviously you can, then those cores can be kept, some cores can be kept waiting while others complete. So there's actually a lot more parallel communication required in diffusion Monte Carlo. There's communication needed actually at every step to compute that average energy and update the population. So then what are the accuracies of this method? So I'm showing here some results for the G1 test set published in JCTC 2012. So this is a benchmark test set in quantum chemistry. And also I'll talk about the variational Monte Carlo results as well. And what was done in this approach was to optimize the coefficients in front of the determinants in large determinant expansion. So what we have here on the vertical axis is the mean absolute error, so smaller is better, and we would like to get below 1 kcal per mole. So that's chemical accuracy. So that's a good target for a lot of quantum chemical methods. Not sufficient, of course, for all the science we'd eventually like to do. And what's shown here, this is diffusion Monte Carlo with a single determinant, and it's 3 kcal per mole, mean absolute error. And then what's shown here, this is an increasing number of determinants in the trial wave function, and these get steadily more accurate results. And so with a sufficiently sophisticated wave function, one can get very accurate results below this target accuracy. And one thing I'd also show here, right, as we also saw for that carbon-2 result before the break, the variational Monte Carlo results are also improving as we have more sophisticated wave functions. But we see here, whereas diffusion Monte Carlo is getting us 3 kcal per mole error with just one determinant in this test set, variational is actually much worse. It's about 13 or so, so much less good, and improving the wave function will be much more important there. We also see, it'd be remiss not to mention, if we do high-level quantum chemistry and take care with the basis sets and advanced methods, we get extremely good results with couple cluster. If we use less sophisticated methods or MP2 or different density functionals, of course, our mileage is different and we get less good results. So those are some chemical results or results from molecular systems. Let me now just sort of talk through some examples in solid state systems. So first here I show on the left some results applying diffusion Monte Carlo with just a single determinant, so sort of the standard recipe that one does in the field without having to worry about orbital optimization or multi-determinants that I've been mentioning. And this was done here for a range of metal oxides. If you look at these are all, of course, components of copper oxide superconductors. And what's plotted here is the energy in the formation enthalpy for these different solids. And we have the fixed node diffusion Monte Carlo result in red, which we see is very consistently small errors. And of course, we can get different errors with other methods. And also in this case, and it's important we don't only look at the energy or any one property in these calculations, we would like all the properties of our system to be very accurate. So here we have the lattice constant, which is also done, and the red is the diffusion Monte Carlo result. And we see it's very accurate for these lighter oxides, but there is seems to be an increasing trend here. So by the time we get to lanthanum oxide, there's maybe a % error. And it wasn't looked at in the study, but maybe this is the nodes. It could also be the pseudopotentials that we use. This was a pseudopotential study. Another area where the standard method, quote unquote, of just using a single determinant for solids works very well. There's been a lot of interest over the last few years, is in the binding of two-dimensional materials, van der Waals systems. And this is the case shown here for phosphorine, where there's actually some very interesting results. So one can look at the stacking and the binding energies from diffusion Monte Carlo. And interestingly, this is analysis of the charge density in the system. What we're seeing here actually was that the charge density is redistributed somewhat differently from what other theories were predicting. And so that's a very intriguing area, I think, worthy of a lot more investigation. And then finally, and actually I added this because I had an email question on the topic. So the question comes, what if we want to eventually study a system which is clearly going to be much too big or much too complex to apply quantum Monte Carlo to? So an example of that would be, could be if we need to do dynamics and look at structural properties, how they evolve in time. And that's much too expensive to do with the diffusion Monte Carlo for a general system today. But there has been some work actually looking at this and using diffusion quantum Monte Carlo to essentially validate and then justify the use of specific density functional methods, for example. And I think that's a very good way forward in this area. And so what was done here, this was looking at the properties of liquid krypton at pressure. So there's not so many experiments here, and we'd like to have really accurate predictions. What was done was to do some ab initio molecular dynamics with different functionals and then recompute the energies of selected configurations with quantum Monte Carlo. So here in this black, we have energies from the local density approximation. And if we recompute the energy with quantum Monte Carlo, we see here there's a lot of scatter. And the surprising thing in this case was that there was a density functional that seemed to do a very good job matching this up. This is the AM05 functional, and then clearly one would be justified in using that much more extensively on systems where one couldn't afford to do the quantum Monte Carlo. So that's an example of using QMC to validate the use of a cheaper method going forward for larger or more complex systems and properties. So just by analogy to what I did with the variational Monte Carlo, let's now think of the pros and cons of diffusion Monte Carlo, and I've also flagged up the errors and approximations here separately as well. So what are on the pro side? Well, on the advantages, well, even with very simple trial wave functions, as we saw for the solids, we can get very accurate results, simple trial wave functions, and importantly, they're usefully accurate. They're a nice step up in accuracy over the other electronic structure approaches we have available to us. They map well onto computers, of course, and as with variational Monte Carlo, there are paths forward, some available now, some that are research topics, to improve the quality of the trial wave functions and then systematically improve the results. So this is a very promising route forward. But there are some disadvantages. First of all, unlike variational Monte Carlo, we never get to put our hands on the trial, on the exact wave function or the projected wave function. That's sort of encoded as a probability in the simulation. And so there are some difficulties here getting to non-energy observables or observables that don't commute with the Hamiltonian. Definitely another disadvantage is that it's much more expensive than variational Monte Carlo. It's easily an order of magnitude. You could argue 2 orders of magnitude for some systems. And also the time step we need to take to keep those errors small does increase as we go to higher effective Z elements. So then all that adds to the cost of the method. And as I mentioned, for variational Monte Carlo, for periodic boundary conditions, one needs to do finite size scaling. Just to recap on the sort of errors or approximations, and I'd like to stress here, there really aren't very many of these, and we can test them. So this is a sort of still an advantage of the method, but we need to take care of them. And the most important one to bear in mind is this fixed node approximation, where we take the nodes from an input trial wave function. And this error is variational. So our energy will always be above the true ground state energy. And so we can test it, but that is a source of approximation. And then another error, which is not sort of fundamental, but we do need to be very, very careful about and make sure we converge it, is things like the time step error in the calculation. And as we'll be hearing next week, we need to do some special treatment for pseudopotentials. So now I'd like to touch on some practicalities, and this is a little bit of a grab bag here, but I'd like to start making connection to practical calculations. So let's recap now what our sort of overall QMC pack workflow, sorry, Monte Carlo workflow is going to look like. And you'll see there's just like an extra block at the end here. So we're going to do, the best electronic structure or quantum chemical calculation that we can do in, the best basis set and so on to generate the input trial wave function, particularly the determinant part and the fermionic part of our trial wave function. We're then going to pick a Jastrow function, and then we're going to do the optimization of that wave function. We will likely just optimize the Jastrow part if we are going on to do diffusion Monte Carlo, but as we've shown, there are routes to optimizing more of the wave function. We would then normally do a production variational Monte Carlo calculation. This is cheaper than diffusion Monte Carlo, so it doesn't add much to the overall study. And then we do a production diffusion Monte Carlo calculation. And of course, the first time we do this for a particular system, we have to optimize the efficiency of the variational Monte Carlo. And importantly, we need to study things like the diffusion Monte Carlo time step. And on that topic, one thing I'd really like to emphasize, I remember when I was first learning quantum Monte Carlo methods, I was thinking, well, hang on, there's all these different ways of setting up the calculation. And the key thing to remember here about statistical approaches, not just quantum Monte Carlo, is that any choice that influences statistics is actually something that we can test. And it's just a good exercise to go off and test these things. And the key thing is, if in doubt, you can always choose to run longer in your simulation and get better statistics. And so the error bars will reduce and you can be more confident in the results. And so of course, they're less dependent then on any choices you made. So other examples of things that one can test, if one is worried about the accuracy of trial wave function optimization, well, you can put more configurations into the optimization and see if the results change meaningfully. If you're worried about equilibration, you can allow for more equilibration time or just throw off some results at the start of the run. And then ultimately, and this is a key thing with all statistical methods, one can do completely independent runs, even on different computers if one wishes to, and the results should agree to within the error bars, at least with the probabilities given by the error bars. So we can test everything that we're doing in terms of statistics in these methods. And one thing I'd also like to stress is that the statistical properties come from the algorithms, the physics, and the elements that are being studied. So for example, if we work everything out for, let's say, bulk silicon, actually, no, let's do graphene. We're going to do graphene, and then we're going to stretch it. Well, everything that we've learned about doing the statistics for the unstretched graphene would then apply to a small perturbation of that system. So we wouldn't have to redo all of this just because we made a small change to the system. So now I'd like to start throwing out some actual numbers that we might see in simulations. These are definitely very hand wavy, but this is just to provide some sort of a guide that, for what we're going to touch on in the following weeks. So this is very much rough guidance for what we might see in current simulations. So what might a time step in variation of Monte Carlo be? Well, maybe about a half an atomic unit. How long might it take to equilibrate? I think even 100 steps is pretty generous. But one key thing I mentioned about dividing the run into some blocks for convenience. Well, if we're going to compute statistics on the blocks, we'd better make sure we have a good number of them to get our error bars. And I've touched on optimization several times, so I don't want to dwell on that. In diffusion Monte Carlo, it's important that we have small time steps. And so it's very typical to see like a 0.01 atomic unit time step. I had that in examples that I showed. And that's needed for accuracy and also stability of the runs. We saw that the warm-up or equilibration time might be a bit longer, so maybe a couple of hundred steps here. And importantly, it's really crucial that we have a sufficiently large number of walkers in our diffusion Monte Carlo runs. So that's easily thousands, could be tens of thousands. And one thing that we're going to touch on next week is this issue of correlation or autocorrelation between samples in our Monte Carlo. If we make very small time steps, then the properties that we get aren't, in our samples, aren't independent from each other. And so we need to, when we compute error bars, we need to penalize them by the factor to do with the correlation period. And for variational Monte Carlo, this is not too big a deal. It's typically a few moves, few steps. But in diffusion Monte Carlo, this can actually be quite long because of the much smaller time steps. So when we compute error bars in diffusion Monte Carlo, we're going to have to bear this in mind and factor it in properly. And we'll do this over the coming weeks. Just a note here on the wave function quality. I said several times we should do the best one that we can afford. What should they look like? Well, here's sort of a rough guide. If one's doing a molecular calculation, we're talking about triple zeta basis sets. Ideally to have some diffuse functions, something like that. And this is actually shown in this wonderful figure from this chemical review paper. So this is the energy of the hydrogen fluoride dimer, energy against basis set, done in couple cluster with perturbative triple, so gold standard quantum chemical method. This, of course, is a basis set method, and we see that the energy that comes out is very strongly dependent on the basis set. And so in those methods, it's important to do proper extrapolation. Fixed node diffusion Monte Carlo operates in real space, and it's much more weakly dependent on the basis set. So we just need to make sure that we use at least a reasonably good basis set here, and I'd really encourage the use of the largest ones that we can afford. In plane waves, if we're going for quantum espresso, that typically means using very high plane waves as well. And the key point here is that if the underlying quantum chemical or DFT calculation isn't converged by more than, let's say, 0.1 EV, we're asking an awful lot of the Monte Carlo to converge better. It's much better that we can converge the quantum chemical or DFT calculation to 0.001 EV. So then the Monte Carlo has got a very good wave function to work from. And here's some other notes and numbers that we might see. Just now a note on some sort of accessible system sizes to sort of put us on the right page. And rather like the accuracy, this is a difficult question to answer because, of course, it depends. And of course, if we wanted could accept a very large statistical error bar, we could run really any system size, so 10,000 electrons. But to do some science and just to sort of get us on the same page here, I thought it might be useful to jot down a few electron counts for different scales of calculation. So perhaps tens or up to 100 electrons we can certainly do on our desk. Beyond that, we eventually have to transition to some sort of departmental cluster at the end of the corridor, and eventually to sort of some computer with the proviso that many of the calculations I showed last week that were done on supercomputers many years ago would now actually fall in this smaller scale because of the lower electron count. So just before I want to wrap up, let me touch on some topics or mention some topics that we didn't cover today that are important, but that we'll be touching on later in this workshop. So I mentioned a few statistical properties and quantities here. We're going to be revisiting those in later weeks. We've already mentioned student potentials a few times. We had a couple of good questions on those. And in about 5 weeks, I think we're going to be hearing about how to design and test quantum student potentials very specifically for quantum Monte Carlo, and actually the available library of potentials that we have to use. And then also I've touched on finite size effects, so the periodic boundary conditions and the finite size scaling that we need to do there. There's a few other topics here. I won't read them all out. If you're particularly passionate or wondering about any of these, I'll mention that we did touch on many of these actually in our workshop 3 years ago, and the slides for those are actually online if you go to the QMC Pack GitHub repository. So you can also take a look there if you're particularly passionate about learning about excited states, for example. There's an example there. So then just to summarize, and I'll be happy to take questions. So I've introduced 2 complementary quantum Monte Carlo approaches, variational and diffusion quantum Monte Carlo. Variational quantum Monte Carlo is the simplest, I'd say most elegant, and it places all the emphasis on the choice of the trial wave function. So we have to choose wisely, and I outline some ways of optimizing increasingly sophisticated trial wave function forms. And then secondly, there's the diffusion quantum Monte Carlo. I think that's a projector quantum Monte Carlo, so it is much less dependent on the input trial wave function. Of course, we have to make the fixed node approximation when we apply that. So it's a much more powerful approach. It's more accurate, but it's also more expensive and has limitations that I've just summarized. So that's all I want to cover today. Let me just point out that next week, we'll be actually using the workshop virtual machine and starting to run workflows of electronic structure calculations and also doing some statistical analysis. So I look forward to seeing everyone next week and also on the Slack channel, and I'll be happy to take any questions now.
Okay, Paul, there are a couple of questions. First one, very theoretical, and then one much more practical. So this is from Yuha. He asks, has the tiling theorem been proven, or is it more like a common observation?
The tiling theorem has been proven, and it's discussed in at least the Reviews of Modern Physics paper, probably some of the other more recent reviews as well. The proof is actually quite simple, so have a look there. It's a real theorem.
Next question is from Anuhab Haldar. Hopefully I got the name reasonably well. If the total number of walkers is less than about 1,000, then is the number of cores within a near unity factor for that for good parallelism? Okay,
that's a good question, and it's to do with running efficiently. So if you have access and start running quantum Monte Carlo on a machine with a large number of cores, the trick is to make sure you have as many walkers per core, right? And that avoids the concern with load balance. There's other ways around this, such as using a form where there's weights added to the track with each walker, so one can use a fixed population of walkers computationally. But the key point is to make sure you have a large number of walkers. And this actually also helps with additional errors in the diffusion Monte Carlo as well. So there's not really a penalty there. It's well worth doing.
Okay, a follow-on question. Is there any rule of thumb for what is large? For example, 10 to 100 walkers per core?
Okay. So I think we're starting to, we can actually go down a little bit of a rabbit hole here. The key, actually, I want to refer back to when I said about testing choices that influence our statistics. We can also test things like the configuration of our calculations. So in the event running is running Monte Carlo on a larger machine, I would suggest trying a number of different configurations, and you'll be able to see the different efficiencies with which they can run. Of course, the calculations do have to fit in memory on the machine, so that could be a consideration as well. So generally what one can do is obviously adjust the population to make sure that it fits, and then you're ready to run.
Okay, we don't have any other questions posted as of now. So I'd like to encourage anyone who has questions about this last section, focus mainly on diffusion Monte Carlo, to post them. But in the interim, I'll ask one question. And that is, Paul, could you just comment a little more on just some good application areas for quantum Monte Carlo methods? So if the audience is thinking about, okay, maybe I want to do some project, answer a science question, what are some good problems that quantum Monte Carlo is especially well suited for?
Okay, that's a great question, Jaron. And I think many of our following weeks are going to be touching on this as well. Well, actually, I think I may have hinted at some molecular applications here. So we see in, that compared to coupled cluster methods, we have much weaker basis set dependence. And one advantage that diffusion Monte Carlo has over at least conventional coupled cluster for molecular systems is that we can treat so-called multi-reference systems very well. And this is the point where coupled cluster tends to start having difficulties. So there are a lot of sort of molecular applications that could be done. There's a large number of sort of quantum chemical test sets that are out there that haven't been tackled with quantum Monte Carlo yet that could provide some hints. That's sort of on the molecular side. Actually, as I have the review here, weak van der Waals binding has been is a troublesome bugbear for a large number of electronic structure methods. So binding of various moieties together is an interesting area to work on. And then on the sort of the more periodic side, one area which I think is really ripe for a lot more applications is two-dimensional materials. There's already a variety of quantum Monte Carlo results showing interesting differences from some prior predictions that have been made in the literature. There's a huge experimental interest in the phenomenology of 2D materials as well right now. And of course, one has the advantage that a 2D material has fewer atoms and electrons in it than a bulk 3D material. So that actually can bring down the cost of the calculations as well. So I think that's also a particularly good area to work in. Any other questions, Jaron?
No, no one has posted any other questions that I can see in the chat.
All right, well, thanks everyone for those questions, and thanks for joining today. As I said at the start, we'll try and get a recording of this up fairly promptly. And as I sit here, I look forward to seeing everyone next week when we tackle workflows and some of the statistical analysis. If you think of any questions in the interim or have some trouble with the virtual machine, please post on the workshop Slack. Thanks very much.